Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to talk about solubility equilibrium. And what solubility equilibrium deals with is our insolubles. So we might have something like silver chloride that if you know your solubility rules, you know that chlorides are usually soluble except if they're paired with silver, mercury, and lead. And it's pairing with silver here. So this is an insoluble. And what some students think at this point is that it never dissolves and forms its ions at all, okay? And the truth is it does it a very, very tiny bit, okay? So for the most part, we can say that it doesn't dissolve, okay? But in reality, when we get into solubility, we have to kind of be very specific. It says, well, it does dissolve a little bit, but most of it does not. So the story goes something like this. As we sprinkle a few crystals into the water of silver chloride, maybe the first couple crystals will create ions, okay? But a majority of it will not dissolve, and you'll just have a pile of solid silver chloride at the bottom of your solution. It won't dissolve. So like over 99% of it will be just silver chloride undissolved in the water, okay? But the truth is a very, very tiny little bit will dissolve, okay? And this is all dictated by an equilibrium constant, and that equilibrium constant is going to be called KSP, where the SP stands for solubility product, like how much of this product can be soluble, okay? So you can see I got AQs on this side, but I have a solid on the left-hand side. So what we're going to do is we're going to write the equilibrium expression for KSP. And remember, that's always going to be the products over your reactants. So our products are silver ions and chloride ions. It's typically supposed to be over the reactants, but we have a pure solid or liquid. And whenever you have a pure solid or liquid, it's not included in the equilibrium expression. So this is just it, okay? So KSP tends to be kind of like an easier type of problem, way easier than dealing with buffers and conjugate acids and bases. KSP is pretty simplified because you're really only worried about the right-hand side of the ice chart. So if I was to make an ice chart, because this is in equilibrium, I am not going to pay attention to the left-hand side at all, okay? Now, there's two styles of problems that you can get. One where I give you the concentration of the silver or the chloride ions and you figure out this whole chart and then calculate KSP, or I give you KSP and then you figure out these concentrations, okay? So in the long haul, we're going to deal with this whole chart, but this first problem is just going to be dealing with going back and forth between these first two boxes, either molarity of ions or the KSP, and then you should be able to get the other. Okay, so what I'm going to do is I'm going to start with the molarity of ions and see if you can calculate the KSP. So let's say the prompt said something like this, okay? You sprinkle in some silver chloride in here, and there's a pile at the bottom, and then you stick a probe, and you measure the amount of silver ions, okay? And it comes out to be 1.35 times 10 to the negative 5, okay? So that's going to be kind of like your given. So I'm going to box that in as a given, okay? And what I want to be able to calculate is the KSP value from the molarity of just one equilibrium position, okay? Well, I can figure out this ice chart because if I sprinkle in some silver chloride and it creates some silver ions, well, it's also going to create some chloride ions. If this goes from 0 up to 1.3 times 10 to the negative 5, then I know this went up 1.35 times 10 to the negative 5. And because of the 1-to-1 ratio, I know this went up 1.35 times 10 to the negative 5, and that this is going to be 1.35 times 10 to the negative 5. And I'm just going to go ahead and plug those values in to the equilibrium expression. So KSP is going to be equal to 1.35 times 10 to the negative 5 2 times, okay? So really my calculator, I could just put 1.35 times 10 to the negative 5 and then square it. So I'm going to go ahead and do that now. I'm going to do 1.35 times 10 to the negative 5, and then I'm going to square it. And that comes out to be a KSP that's going to be equal to 1.82 times 10 to the negative 10. Okay. Now, I could have done this problem in reverse and give you KSP, this value, okay? And then you had to calculate the molarity of the ions, okay? Now, the way I would do that problem, if I was given the KSP value of 1.82 times 10 to the negative 10, what I would do is I'd say, okay, this is going to go up X, and because of the 1-to-1 ratio, this is going to go up X, this is going to be X, this is going to be X, and I'm going to plug those values in. And I'm going to say that that's equal to 1.82 times 10 to the negative 10, okay? And when I take the square root of that, I will get back to these concentrations of 1.35 times 10 to the negative 5. So I can start out by giving you the concentrations of the ions, and you have to figure out the KSP, or I could give you the KSP, and you can fill out this ice chart to get to the molarity of the ions, okay? And that's how you do this problem, okay? Now, this one is kind of easy because everything's a 1-to-1 ratio, okay? What if we get a problem that's not 1-to-1 ratio? It becomes a little bit more complicated, but overall, still, I think much easier than buffered solutions or anything that deals with conjugate acids or bases, okay? So let's say I'm going to do the next problem. Instead of having silver chloride in there, let's say I have calcium fluoride. So I'm going to put some calcium fluoride in here. And the same thing's going to happen. Sorry, I'm blocking the camera there. As I sprinkle it in, the first couple ions, okay, will dissolve. Now, calcium's a positive 2 ion, and every 1 calcium ion, I'm going to get 2 fluoride ions, okay? So the first couple crystals might dissolve, but after that, you're just going to get a big pile of calcium fluoride at the bottom of your beaker, undissolved, okay? So we're going to set up an ice chart for this because this is not a 1-to-2 ratio. I'm sorry, it's not a 1-to-1 ratio. It is a 1-to-2 ratio. Our equation should look something like this. So AQ's on the right-hand side, solid on the left-hand side. You'll see that take place for all of them, okay? All these KSP problems. And what I want to do with this problem is I kind of want to start right here and then work my way all the way across. So I would probably copy this in your notes right now because I think this is kind of like what most chemistry teachers are going to ask of their students. College board, if you're an AP student, okay, or if you're at the university, your college professors will probably want you to know how to go from one end all the way to the other, okay? So in this problem, I'm going to give you the KSP value of the calcium fluoride. I'm going to write it right here. KSP is equal to 3.9 times 10 to the negative 11. So as you can see, with a really, really small equilibrium constant, okay, this hardly shifts to the right at all. And you're going to notice that most of your KSP values are really, really small numbers. Times 10 to the negative 11, 12, 13, 20, you name it. It's not dissolving a whole lot. But anyways, here's my given, 3.9 times 10 to the negative 11. So my next step is to figure out the molarity of the ions, okay? And the way I'm going to do that is with an ice chart, okay? I know that the calcium ions, if it goes up a value of X, then the value of the fluoride ions have to be double that, okay? And that's why I'm calling it 2X. And you're going to see that this coefficient plays a role in these problems in 2 different ways. The first way is right here because of stoichiometry. So this ends up being X, and this ends up being 2X, okay? And that's because of stoichiometry and this 1-to-2 ratio. And then you see it pop up a second time in the equilibrium expression, okay? So the equilibrium expression, KSP, is going to be equal to the value of the calcium ions multiplied by the fluoride ions, and it's going to be to the second power. Because when you're dealing with equilibrium, in the equilibrium expression, coefficients are exponents. And we haven't dealt with exponents in a long time because we've been working with acids and bases, and everything's been a 1-to-1-to-1 ratio, all ones, okay? Well, the coefficients are popping back up, and they're going to hit you in two places, once for stoichiometry and once for equilibrium, and you can't forget that, okay? So now it's just kind of plug and chug. I'm going to take the KSP value, which is equal to 3.9 times 10 to the negative 11, and then it's going to be equal to calcium ions times fluoride ions squared. Well, the calcium ions are X, the fluoride ions are 2X, and I need to square that. And this is where a big mistake happens. Some people say that this 2 only counts for the X, but it counts for the X and the 2, okay? And 2 squared is going to end up being 4, okay? Now, X times X is going to be X squared times another X is going to be X cubed. The common error that I see is some people call this 2x cubed instead of 4x cubed because they did not distribute the exponent within the parentheses. So be careful right there. So 4x cubed is equal to 3.9 times 10 to the negative 11. So in my calculator, I'm going to take 3.9 times 10 to the negative 11, and I'm going to divide it by 4. And then I want to show you a button that you're going to probably have to use on your calculator. So 3.9 times 10 to the negative 11 divided by 4, okay? So I just kind of want to show you what I did right there, okay? Now I have to take the cube root of that, okay? So what I'm going to do is I'm going to come in here, and let me get it, hopefully give you a clear view of this. I'm going to come around on the camera on the other side, help out, okay? So here we go. So what I'm going to do is I'm going to hit this math button, and it's going to give me some options, okay? And what I want is that fourth option, which is the cube root, okay? So that gives me the cube root, okay? And I have to put in my answer. So I'm going to hit the second button and then answer. And you can see that I'll get this value when I hit enter of 2.14 times 10 to the negative 4. So once again, I hit the math button and then option 4 to get that cube root. And then I just plugged in my answer. So X is going to end up being equal to 2.14 times 10 to the negative 4. And that's equal to X. So I know that the concentration or the molarity of the ions, okay, the calcium ions are going to be 2.14 times 10 to the negative 4. But the fluoride ions are going to be double that value. So I'm going to take that value of 2.14 times 10 to the negative 4, and I'm going to double that. I guess you could probably do that in your head of 4.28 times 10 to the negative 4 is the concentration of the fluoride ions. So I'm going to plug that in here. So the concentration of the calcium ions was equal to 2.14 times 10 to the negative 4 molarity. And then the fluoride ions is double that at 4.28 times 10 to the negative 4 molarity ions. Okay, and I'm now going to continue to go on and get to the molarity of the compound. So once again, I'm going to use this X value, which is the molarity of the calcium ions. And I'm going to write molarity as moles per liter to help with my math here. So the calcium ions have a molarity of 2.14 times 10 to the negative 4. And what I'm going to do is I'm going to convert the moles of calcium ions into moles of the compound being calcium fluoride. And if I look here, the ratio is 1-to-1. So I guess that math is pretty easy. It's just going to be the concentration of the calcium fluoride is just going to be this really low number of 2.14 times 10 to the negative 4 molarity. Not much of it is going to dissolve. 2.14 times 10 to the negative 4. That's like 0.000214 moles per liter. So hardly any at all, okay? But that's going to give me the molarity of the compound. Now, if I want to go to something called solubility, the units are different. Now, they're both concentrations, okay? It's just that molarity is in moles per liter, and you can see kind of how we get moles per liter here, okay? Where solubility is grams per liter. Well, if I want to switch from moles per liter to grams per liter, all I need is the molar mass of calcium fluoride. So what I'm going to do is I'm going to change the moles of calcium fluoride into grams of calcium fluoride, and I'm going to plug in the molar mass, okay? And the molar mass of 1 calcium and 2 fluorides is going to give me a molar mass of 78.1, okay? So if I do this work, the moles of calcium fluoride are going to be canceled out, and I'm going to have grams per liter, which is a solubility number, okay? And when I get that, I get a number of 0.0167 grams per liter for the solubility of calcium fluoride. So I'm going to put that in here, 0.0167 grams per liter of my compound calcium fluoride. Okay. Now, you could totally work this problem backwards. Okay. I could give you this number, and then you could figure out the molarity of the compound, and then figure out the molarity of the ions, and then plug those molarity of ions into the equilibrium expression to get back to your KSP value. So as a student, you need to be able to work this forward, okay, and backwards, okay? So I would start out by finishing this by taking this number and seeing if you can come back to this number. And if you can, you have probably mastered solubility equilibrium. And if you found this content helpful, please give it a like and subscribe. When you add that comment, it really does push this information out to other students that might be interested in learning chemistry.